Today, I will be talking about subspace learning for one-class classification. I will start by introducing myself, a bit about my group, Tampere University, and then we talk more about subspace learning, one-class classification, some of the applications and the methodologies that we have developed here in our group. So my name is Fahad, as you all know now. I'm a postdoctoral research fellow here at Tampere University, and just a brief introduction about the Tampere University is that it was formed in 2019 through a merger between University of Tampere and Tampere University of Technology. So before it used to be two universities and one other institute, so they all joined together. And we have three campuses here, City Center campus, Harwanta, and Kauppi campus, and I am part of the Harwanta campus. And it's quite big university, and our group, Sami's research group, is led by Professor Monsef Gabouj. We have 4 research associates, a few doctors, 2 postdocs, 23 PhD students, 5 master students, and the core of our research group is that we develop novel machine learning paradigms, and of course we also focus on signal processing, biomedical signal imaging analysis, computer vision, and video compression. Machine learning is a big part of our research group, and we develop core and novel techniques and paradigms for machine learning. And I will be talking about one side of the machine learning and the methodologies developed in our group. And as a fun fact, why I am in Tampere, it's because a lot of good things, but the background photo you see here is the photo that I took last night. So you see a lot of good auroras and northern lights here in Tampere. So let's start with the formal presentation, and I would like to start with the very basic definition of what is data classification, just to give you an overview of the methodologies that we'll be developing, which I will introduce soon. So in data classification, the overall goal is to define or infer the hidden function that map input to the output. So for example, when an email comes to your inbox, it is classified either to a spam or it goes straight to your inbox. So this kind of classification you see in your life on day-to-day basis. You may have noticed this on your phones, like when you categorize or the algorithm categorizes the images for you. You may have seen it some, for example, in your normal phone, like a spam messages, or think about any specific entity classification problem. So in practice, what in machine learning classification problem, what is done is, how do we create this algorithm which would classify the incoming data into predefined set of classes, and that's overall idea of basic data classification. And how this is done in practice is that we have a certain amount of features, like we have the numbers that represent those instances, and then we try to infer the function that during the test that would help us in classifying the test instance. So for example, if we give a very basic example of how would we classify oranges and apples, so certain amount, the features could be like weight and size, for example. So those are our features, and then the class would be that if it belongs to orange or apple. And in this case, what we would like to do is draw this black line, which you see, and then of course during the test, if anything falls on the below the line or on one side of the line, it will be classified as orange, and on the other side it would be apple. And of course you can generalize this kind of binary classification problem to any task, and the features can be much more. This is a very simple example, so we'll come more to what are features and what are the challenges that we need to solve here, and so on and so forth. But this is just to give you a very basic overview of features and classes, or the features would be considered as our data in this case. Now, to To move along and make it slightly challenging, I usually ask this question in my presentations, that what is common in a forged painting, rotten apple, defective robot, and a stroke? So you might be wondering that it might be also a classification problem. Yes, indeed. Like, for example, the idea is that can we classify if the painting is forged or is it real? Or, for example, in the rotten apple case, can we classify on the basis of the image if uh, the apple is rotten or is it fresh? And for the robot also, if it's a defective robot or is it working? And similarly for the stroke, if there are some indications from the biosignals, for example, that the stroke is coming, or some abnormality in the health of the brain is coming up. So as you can see, that these kind of challenges might not be trivial to solve. And why is it that in some of these examples, you may notice that collecting the data would be a big challenge. So for example, for the apples, well, we may have some data from the rotten apples that we can extract some features from that and train our model. But imagine getting the same data for somebody with for the stroke example, like how would we make the person fall ill or having a stroke, and then only we will collect the data. So it's not that straightforward to collect the data for these different tasks. And also one other challenge would be that the number of possibilities from one of the category could be huge. So for example, in case of the robot not working, it might be possible that there are so many different ways that the sensor would not work, that collecting all those possible instances for that category would be challenging. So here, I just want to give you an idea of the binary classification problems in which from one of the class, the data is not available. And also to give you the hint that in some of the applications, it might not even be available at all. So then in those cases, what to do? Like, for example, it if it is costly to collect the data from one of the categories, and by cost, it can be a cost related to the health, or it can be financially costly, or it can be, for example, that the machine has to be damaged so that we collect the data and to create the model for those kind of problems. Because remember that in machine learning, training a machine learning model requires some data from the categories that needs to be modeled. And then we saw earlier that, for example, in the apple and oranges cases, we have only two set of features, like weight and in the size, but the features can be very high dimensional. And also, how would we decide that what features are good enough for the data modeling? And also, you might be aware of this term curse of dimensionality, for example, that the higher dimensional data, the crazier it gets in terms of creating a model for that. So these are the two challenges that can be faced when it comes to this binary classification problem. So in order to solve this issue, then we would go towards something called one-class classification. So the idea in one-class classification would be that we would train the model by using data only from one category, and hope that it learns or it creates the model in a way that during the testing, it would accurately classify the data from the other class as well, or other classes combined together to be known as a negative class. So technically, one class classification is a binary classification challenge in which the data is used only from one class during the training, and during the testing, then we have two classes. So as you can see, we have the training samples only from one class. During the test, then everything belonging not to that class is considered as the negative class or outlier class. So positive class or target class versus negative class or outlier class. That's the main idea of during the testing in one class classification. So the idea here, or the question here, is that can we create a methodology where the subspace learning and the model learning complement each other for improved one-class classification performance? And can we provide a framework which would unify the subspace learning methods for SVDD? I will introduce some of the keywords soon, but what we would like to do is that one-class classification usually models the data in whatever is given to it in the original feature set. But how can we infer more discriminative features, or how to reduce the dimensionality of the data in a way that it complement this one-class classification algorithms performances? And of course, then we would like to create a framework which would unify all these kind of methods for something called SVDD, support vector data description. I will describe this in detail in the next slides. So this is the basic concept of on the right hand side the subspace learning, and on the left hand side data description. So in data description, what we would like to do is create a closed boundary around the target class data, and the assumption is that we have all the data only from one class. And during the test, anything falling outside that boundary would be considered as outlier class or the negative class, and anything falling inside that closed boundary would be considered as the target class. And then on the right side, you see some sort of transformation from, for example, 3-dimensional space to a 2-dimensional space. And what we would like to do here is try to create an iterative process where the projection of the data from the higher dimension is from the higher dimension to a lower dimensional space is done in such a way that it complements the data description, for example, in this case, on the left-hand side. So what we would like to do is projection and data modeling. So this kind of problems are formulated in the following way. So we would have this objective function that we want to minimize, and it has a radius, and we would introduce a slack variables which are controlled by this parameter c, and the slack variables define how much outliers are expected in the training set. And of course, we hope that everything is enclosed in the smallest possible boundary. Here we talk about the linear cases, but of course, all these methods that I will talk about have an extension towards the nonlinear methods as well, because in reality, the boundary is very flexible and not just the linear sphere. So then we use some Lagrangian of the problem, taking some partial derivatives. I will not go into a lot of mathematical details, but when you maximize the Lagrangian of this problem, which is given here, as you see, it gives you some alpha values that we will talk about soon, and then they define the position of these instances in the data description. But also please notice that also in the previous equations and in this one, we have introduced this parameter, this matrix, sorry, Q. So Q is the projection matrix that will map the data from the higher dimensionality to the lower dimensionality. And it should be done in a way that we should be able to form this closed boundary in a more compact way, and it should lead to better performances for this one-class classification task. So as we saw that, for example, when we maximize this equation, after we would put those derivatives and everything, the idea is that we would get some alpha values, and those alpha values would then define the position of the data points in the data description. And what does it mean? So it means that we need only few samples which would describe this kind of closed boundary. So this is a typical problem which is solved as SVDD, support vector data description. But in our work, we would also project the data to this lower dimensional space and then try to encapsulate this in this boundary, and also the boundary has to be created. So it's an iterative process data projection, and then encapsulating. So as you can see on the right hand side that the data from, for example, here in 3D is projected to a lower D, and then we would try to encapsulate it in a closed sphere, and then the sphere would be considered as our model. So anything inside the sphere would be considered as the target class, and anything outside the sphere would be outlier class. And as I mentioned before, these alpha values define the value of the position of the data points in that data description. So in this case, as you can see, that all the points which would be lying inside the closed boundary would have the corresponding alpha values as 0, and we could control the amount of the outliers present in the training data, so they will go outside this hyper boundary or closed boundary, and they will be assigned as the value of C, and anything greater than 0 and less than C would be on the surface of this boundary, and that we would consider as our support vectors in this case. So that's the bigger picture of all these methods that I will be talking about in the next slides. We also introduced some regularization terms for this kind of subspace learning and data description. And you can see this term C, which is the trace of the data in the projected space. But we could control what exactly would we want to be in this regularization. So for example, if we put the lambda values equal to 0, then it means we don't do any regularization. If we put it as 1, then it means that all the data in the projected space are selected in the describing the class variance. If we select it as alpha, if lambda is replaced by alpha, then it means that the points which lie on the boundary or which are outside the boundary are considered in the data description, and not the ones which are inside this hyperboundary, because we saw in the previous slides that the points with the points which are inside the hypersphere, they have the alpha value corresponding to 0. And then as a last or the fourth regularization term, we would replace it with the alpha values where the alpha value is equal to C for the corresponding samples. So that means that only the points which are outside the sphere contributes to this kind of data description. Now, we saw in the previous slides that we were encapsulating the data in a hypersphere, and that work was already published back in 2018, something called Subspace Support Vector Data Description. But then we had an extension of that method where we introduced the covariance of the data in the optimization process, and that led to ellipsoidal subspace support vector data description. In this plot, at least, you see the different kind of comparisons of the regularization terms for the SVDD, SSVDD, and ellipsoidal SSVDD. And here you can clearly see that the ellipsoidal one converges much faster. For example, the red line, it already converges at the beginning. So because, as I said in the beginning, it's an iterative process. You have to do the projection and then the data modeling. Here it gave a nice insight of the future works as well. Then we created this graph embedded subspace support vector data description, which got accepted very recently, and we prove that this subspace support vector data description is in fact this can be presented as a graph embedding problem, and it also generalized the previous work that we have done. And also we got a nice insights of its analogy with the PCA, for example. So you can see that in PCA, the data is it's considered the unweighted variance of all the data points from the center value, while the SVDD considers it according to the outliers from the SVDD center data. And also PCA is fully connected with equal weights, while in SVDD we saw that it's connected according to the alpha values. And then, as you remember, if the alpha value is 0, then it means that it's inside the hypersphere. So in that case, they are not connected to any other data points. And also we deduced different solutions as well, rather than only gradient based. So we will see spectral gradient based solution as well. And also here we can introduce the graph that we want to optimize during this optimization process. So it's more generalized form of this subspace learning for one class classification, in particular for supported data description. I will not go into a lot of detail of the algorithm, but just to give you an overview, you can give it your input data. You can select a Laplacian, the kind of graph information that you want to embed. It will be automatically selected. You can decide the learning parameter rate. And also the idea is that we map the data to a lower dimensional subspace, small d. So you can also choose that as a hyperparameter and then some other parameters. And then in the output, you can get the Q, the projection metric, which will be optimized for SVDD, the radius, and also the data description in general. And as you can see that in the algorithm, you can select the kind of solution you want to use. So you can use the gradient-based update, you can use the spectral update, and you can use the spectration-based update. All of these codes are provided in my GitHub repository, so they're very easy to use and ready to use. Currently, they are in MATLAB, but we are working on the Python implementation of this works as well, and it will be available soon for use. But for now, if you are used to working in MATLAB, you can already use them, and the demo is available, and you can make quite good use of this for your projects or any of the challenges you may have, which can be formulated as one class classification problem. And also you can see that we have this minimization and maximization problem as well. So you have the choice to choose if you want to maximize or minimize the Laplacian that you would give as an input. More details you can find in the paper, but let's proceed with the next slides. Now we have this one other variant of the method, which we call it multimodal subspace support vector data description. And the idea here is that how can we transform the data from two different modalities to a common subspace? So imagine that if you have two different sets of feature for a similar instance. So can we use one class classification for multimodal data? So in traditional ways, what researchers would do is they would concatenate the different kinds of features and then they would train the model. But here we project the data from two modalities and we map them to a common subspace, and then we do this subspace modeling. So it reduces the need of multiple models as it would happen for in traditional way for different modalities. And also we reduce the dimensionality of the data. And of course, you can find more details in our paper, multimodal subspace supported data description. Also, the course for this paper are available online. And if you have multimodal data and if the feature vector is given, then of course you can use it for this kind of data description as well. Now I will talk briefly about some of the applications that we have developed or where I was part of some of the works which use some of the methodologies that we have developed. So we have been focusing on the methodology and creating new methods, but from time to time, of course, we also apply them to some of other real world applications, or not only on the standard data sets for proving it as a concept. So for example, in this case, we applied it to boosting rare benthic macro invertebrate text identification for that purpose. So it's kind of useful to identify these rare species in which live underwater. But the problem here is that the rare species does not exist in abundance. So which means that we don't have a lot of data available from those rare benthic macroinvertebrates, but identifying them has some value for the ecosystem. So we designed this kind of framework that can we just have the image and preprocessing, then CNN identification for extracting the features, and then we use our Oneclass classification methods. And then if it would be identified as a outlier, then we send it to biological assessment, and then of course also for manual identification accordingly. And it helped the experts, and of course this is also one application, but if you have a different application of this kind, this can also be used. And also it's worth mentioning that we have already extended this work to a multimodal end-to-end neural network based Oneclass classification as well, which is under review, but hopefully it will be out soon as well. Now, one other it's work which I was part of back in 2016, in fact, during my master thesis, is we used Oneclass classification for identifying railway vehicle from the audio source. So it's also a typical Oneclass classification problem where the not a train vehicles are abundant. So as I mentioned in the beginning, that the idea of Oneclass classification is that one of the class is either not available or it's so diverse in nature that you cannot use it during your training process. So all we did here was extract the features from the audio recordings, from the train data only, railway vehicle data only, and then created our model which would accurately classify from the audio recordings as if it's train or not train. For some reasons, it was important in Netherlands to identify the trends, because if they sound a bit high, then they can, it's not legal for the trends to create louder noises for some specific ones. We have also used very recently some of our methodologies for identifying early myocardial infarction. And the idea here is that you have the heart echo data in two different views. So for example, you can see top view and bottom view. And as I mentioned in the previous, one of the previous slides, that you could combine the two feature sets, in this case, to a joint subspace and model it for your classification task. So in this case, we were trying to identify if there is an anomaly in the heart or not, or if the heart beats. So my colleague Aishan, she extracted the features, and then we applied our method, and it worked quite nicely. This work was also accepted recently in one of the conferences, and it's available online, so you can find more details there. Some of the other applications and challenges and some of the limitations of our work. So the methodology is there. We have created a lot of novel machine learning algorithms for Oneclass classification. And now it's time to make use of them. So you can use them, for example, for fraud detection in some banking data. You can use it for any abnormal event detection in some multi-sensory environment. For medical diagnosis, it's of special interest because it's very hard to gather data from non-healthy categories, for example, in the medical field, but it's important to identify them during the test. I've seen some papers where they use it for structural health of buildings through some sensor data, because gathering the data of the damaged building, or if you have a specific building, it's working in a nice condition. So the healthy data has to be fed to the model. And sorry. And for some social media related applications, so we are working on identifying, for example, one specific target tweets, or think about some flag if it has to be raised in social media for some coming input data. So because healthy or the normal one is quite well known, but the abnormal one is, or the anomaly is not known. So this can be used for many of these kind of applications. Some of the limitations that I have identified are the computation complexity. So almost all of the methods that I mentioned in my talk have in terms of O n cubic complexity. So I think there is a need to improve that, and also the risk is very different for different applications. So for example, as we saw very earlier in the slides, that for apple, rotten apple and fresh apple, well, the risk is very low. Like, okay, somebody would just see the apple and visibly also they can see it. But for example, in the health diagnostic, if something is misclassified, then it's the cost might be too high in that case. So I think there is a need to incorporate some sort of risk information in the optimization process of these methods. And yeah, I think that's all from my side. You can find the papers that I mentioned in my talk here, and also the codes are available online in my GitHub. So please make good use of them. Feel free to contact me if you find any issue in the course, or if you have any questions, please let me know. I can answer now any questions.